Hi, nice to meet you everyone. My name is Sergio López, a doctoral student at the Center for Research in Advanced Materials. Today, I am pleased to present my poster titled TiN nanofilms for the generation of thermal dissipation through pilariton-phonons coupling. Let's begin discussing the concept of the polariton. What is a polariton? Phenomenologically, we can describe it as a bosonic quasi-particle found in a state of superposition. This occurs when there is a strong coupling between an excited state of matter and an incident electromagnetic wave. There are various polarized states of matter, such as phonons, excitons, and plasmons. Recent research has reported an increase in the thermal conductivity of materials when polaritonic couplings are generated within them. This is because the transport of polariton thermal energy is more efficient compared to electron medium transport. For this reason, we have selected a material with relatively lower thermal conductivity than other conventional use materials in electronics, as shown in table number 1. Moving on to the experimental section, we began by growing titanium nitride films on a C-sapphire substrate with a 0001 cut, growing the 1-1 plane of tin parallel to the substrate surface. By calculating the lattice mismatch, we obtain a compression value of less 8.81%. The parameters used for the sputtering deposition can be seen in the table number 2. As illustrated in figure number 4, the plasma exhibits a metallic blue color, indicating the presence of nitrogen in the deposit chamber. In the results and analysis section, the micrograph in figure number 5 shows a trigonal symmetry. Surface with dimension of 22.67 micrometers, previously calculated using the Scherer equation, yielding an average crystal size of 23 nanometers, similarly in figure number 6. The average roughness measuring shows a value of 3.2 nanometers. The TiN fields were characterized by width and XRD, revealing an island tip of crystal growth and identify the 1-1 epitaxial plane of deposition. Subsequently, we can observe the Riemann spectrum. In this spectrum, we can observe the along with the is-fitting curve and the convolutions, which denote the TA and LA modes corresponding to the transverse and longitudinal phone bands respectively. Furthermore, we can confirm the preferential crystal orientation of the field through TiN site characterization. The same cross-sectional profile allows us to semi-quantify the film's composition, revealing a variation in the nitrogen percent through the structure, with a lower nitrogen concentration at the upper section compared to the lower cross-sectional height. Using EELAs, we obtain the electron energy loss function, which provides the complex dielectric function consisting of the real and imaginary parts of the dielectric function. The real part being a scalar value, the electric constant. We also calculate the surface plasmon and bulk plasmon. Interestingly, an adjunct observation in our research was the measuring of a certain degree of magnetization in the films. It's important to note that titanium nitride is not a magnetic material. However, in a monocrystalline films, we observe a hysteresis loop. As shown in figure number 20, the literature suggests that it's a non-conventional magnetization, making further magnetic measurements of this material a compelling avenue for continued investigation. Finally, in figure number 13, we present a ellipsometry image showing the optoelectronic behavior of our films across a range of 0. We conclude with the following statements. Epitaxial TiN films were grown on 6 sapphire with an epitaxial relationship between 0001 plane and 11, along with evidence of nitrogen vacancy by EDS. Stransky-Krastanov growth mode with facet was observed. Its spectroscopy demonstrated a dielectric constant value of 5 and responds a different wavelengths. A magnetization of 7 mu per centimeter cubic, a low coercivity corresponding to unconventional ferromagnetism were determined. We localized the T, A, and LA mode with the Raman spectrum. I extend my gratitude to all those who contribute to this research. I would like to sincerely thank my advisors, Dr. Sion, Dr. Herrera, the technicians, Olguin, Dr. Solis, Marco, all the members of the Magnetic Nanostructures Laboratory, CIMAP, and CONACYT. Here are the references used in this poster, and I sincerely thank you for all your interest and attention. Have a great day.